It's on.
It's on? Perfect.
Yeah.
A bit high.
Okay. Okay. Hi everyone. I'm Ivana, and I'm your chair for this afternoon session. And we're going to start with our bingo winner.
Thanks. So good afternoon, everyone. I'm super happy that I'm presenting after the launch. So you are up. So, well, my name is Yaherlyn Diaz. You can call me Yaher. I'm postdoc fellow at the Universidad Diego Portales in Chile, working with Claudio Ricci. And today I'm going to present my recent work, where basically we have been studying the 11.3 PAH feature and their link with the agent parameters. Okay, perfect. So before I start, let's move to the mid-infrared and agents, and a bit an outlier of previous talks. Basically, the nuclear dust in agents absorb part of this intrinsic emission, and this emission is re-emitted in the infrared, and of course, this peak in the mid-infrared. And also in the infrared, we have very interesting and different features, as for example, we can see here. Some emission lines with low and high ionization potential, H2 emission lines, and the subject of this talk, which are the PAH or polycyclic aromatic hydrocarbons. These molecules are carbon-based molecules resulting from the union of some benzene rings. Also, these molecules are very common in our planet because they are part of the life buildings. They are part, actually, of the DNA. But even more important, they are in our coffee. So they are very important, especially for us as astronomers. But in astrophysics, they are very interesting because they can even take 20% of the total infrared luminosity in starburst galaxies. So they can be very, very bright compared with other lines, as for example, H alpha or C2, as you can see here. Also, they can be used as star formation ray tracers in starburst galaxies. However, it's a bit controversial, the link of these PAH features and agents. So the idea of this work is try to understand if we can use these PAH features as star formation ray tracers in active galactic nuclei. And as a consequence of this, of course, we are going to explore any link of the strength of these molecules and agent parameters as the black hole mass, accretion rate, or X-ray luminosity. The question, why we are doing this? Well, because now we have the GWST. So this is just basically to have a benchmark for this amazing telescope. And of course, probably you already see in the archive the last 3 weeks a lot of papers talking about pH. So probably you start taking into account these molecules now. Okay, so how we are doing this? We are using the BAT survey, which is a survey in the X-ray with the Swift BAT telescope. So it's in the hard X-ray band. So we are pretty sure that we have agents. Also, this survey is very nice because we have optical, mid-infrared, and X-ray, of course, observations. But we just took the mid-infrared observation with the Spitzer in the low resolution module. So in the end, we have a sample of 163 agents. So after having our sample, we perform the CD fitting. So we use the PAH fit MC code. So basically, we are performing the fitting of this PAH feature with a Drude profile. So in the end, we have this amazing detection rate for this molecule. I'm not going to talk about the others in this talk because I don't have time. But we can see that for 11.3, we had a very high detection rate, reaching even 96% of detection. So we were able to detect in almost all the galaxies, so which is very nice. And after having this, we have the strength, so we can calculate the star formation rate. And to do that, we use the C correlation 2019, who actually relate the star formation rate and the luminosity of this pH for starburst galaxies. And then we compare this with our estimations using the far infrared SED fitting from Ichikawa's work. Okay, so very quickly, my results. Let's move to panel A. Here. We can see here the star formation rate using the pH. And here we can see the star formation rate using the far infrared estimations. And we can see that when we use the pH, we have an offset. So we are kind of overestimating the star formation rate when we compare with the far infrared estimations. So the question is, why we see this? So let's see if the agent is the responsible of this. So let's move to the panel B when we see the ratio of the star formation rates and the X-ray luminosity. And we can see that there's even a weak correlation. We see that the agent seems to have a role producing this offset in the star formation rate. So to explore this even further, we move to the panel C, comparing the fluxes in the X-rays and the fluxes of the 11.3 molecule. And clearly we see this positive trend. In green, we have only the VNet data point with at least 20 points in each P. So we see that seems to be that the agent has a role there, enhancing the producing the emission of this pH. So I think the takeaway message here, because I don't have time to explain all the details, is that if you are planning to use pH as a star formation rate tracers in agent, be careful. Because the agent has a role there, and it should be taken into account, and some corrections should be done in the previous correlations found. So thank you, and I'm open for questions.
Thank you very much. We have time for a couple of questions while the next speaker comes down. Do we have no mic? Okay, I'll give you mine then. Okay, I don't know.
I can't see anybody. Thank you for your talk. I was just wondering, what is the physics behind the fact that AGN kind of drives up this pH flux? And second question is, have you looked at the other pH features at other wavelengths, and do you see the same trend?
Yes, okay. First question is basically by vibration. So the pH emission is produced by a star formation rate by a very young stellar population. I can show you later the details because I'm an X-ray astronomer, I'm learning. So, but basically it's very young stellar population and a bit of B contribution from a star type B. Regarding the other pH features, I explored them. However, it's a bit difficult to say anything about them because due to the resolution of a Spitzer, we cannot separate between nuclear and circumnuclear. So we are taking everything. So the best that we can do is talk about inner megaparsecs. It's the best that we can do. That's why this is a benchmark for the GWST. The GWST actually help us to properly study this pH, also see this contribution, because in the end they are just a blend or ionized or neutral stuff. And the other pH, it was a bit difficult because I found kind of a correlation, but it was very weak and not significant. So I cannot say anything about them. In fact, there are a few words suggesting that actually these molecules can be destroyed because they have a smaller size compared with the 11.3. So that can be just the consequence of that. But remember, we are observing large scale, so probably this is just a region where these molecules can survive. So, yeah.
And we had a second and last question.
Super brief. What kind of redshift is this?
Okay, I didn't filter it with redshift. I have everything, but I don't have a lot redshift. I'm talking about the highest that I have is 0.5.
Cool.
But I couldn't redshift to see if I can get the same distribution, because since Spitzer is like, I'm taking everything, I couldn't redshift to reach the inner megaparsecs, and the things remains the same. So
We should talk more because this is super interesting results. Thank you.
Thank you. Glad you like it.
Let's give a round of applause and welcome our next speaker, Toby.